Ever wonder how a ship made of heavy steel floats on water? Picture a building taller than a 15-story tree floating in the ocean. It weighs more than 200,000 cars stacked together, and yet it does not sink. Not even a little bit. Even when massive waves crash into its side. The ship stays up. It also stays mostly level. No leaning, no tipping, no falling sideways. So how does this floating metal skyscraper actually work? Our gut tells us heavy things sink. Drop a rock in a pond and watch it disappear to the bottom. Drop a steel bolt in a glass of water and it drops fast. So intuition says a 200,000-ton steel ship should drop even faster. It should sink like a stone. Our gut also says tall things tip over. Think of a tall ladder standing on a wet floor. The higher it is, the easier it falls. A 15-story building on water should be a disaster. A wave should knock it flat in seconds. That is what intuition expects. But the ship does not sink. And the ship does not tip. Physics is doing something our eyes cannot see. Two invisible forces are working overtime. The first invisible force is called buoyancy. Buoyancy is simply the upward push that water gives to anything placed in it. You have felt buoyancy in a swimming pool. The water gently lifts your body as you step in. That gentle lift is buoyancy at work. This lift comes from a famous rule called Archimedes Principle. Archimedes was an ancient Greek thinker who figured it out over 2,000 years ago. His rule has two simple parts. Part 1. When an object sits in water, it pushes some water out of the way. Part 2. The water pushes back up with an equal force. The amount of push equals the weight of the water that got moved. Here is a quick example. Imagine a small wooden block placed gently into a bucket of water. The block sinks partway down. It pushes a small amount of water over the edge. That spilled water has a tiny weight, so the water pushes the block up with that same tiny weight. Now imagine a much larger block placed in the same bucket. The big block pushes a lot more water out of the way, so the water pushes back much harder. This is why a small rock sinks, but a giant cargo ship floats. The key is not just weight. The key is how much water gets pushed aside. Engineers call this the displaced volume. That means the space the ship takes up in the water. A rock is small. It does not displace much water. A cruise ship is enormous. It displaces an ocean-sized amount of water. The trick to floating is not being light. The trick is being big enough to push aside water that weighs more than you do. A steel ship is heavy, yes, but the ship is also full of air. Picture a steel balloon shaped like a ship. The metal walls are thin. The inside is mostly empty air. Air is incredibly light compared to water. So the total weight of the ship plus the air inside is less than the weight of the water it pushes aside. That is the secret to floating. A ship is mostly a big steel bubble full of air. The bubble weighs less than the ocean water it replaces. So the ocean holds it up. This is why even a battleship made of thick steel armor floats. As long as the inside holds air, the math works out. Water gets into the inside, though, and the ship sinks, which is exactly why shipbuilders make the hull as watertight as possible. Floating is solved. Now the next problem. The ship floats, but ocean waves are pushing it sideways all the time. Left, right, up, down. Without help, the ship would rock like a rowboat in a storm. People would get seasick. Dishes would slide off tables. The ship might even capsize. So engineers needed a way to keep the ship level. Their main tool is a spinning wheel called a gyroscope. A gyroscope is just a heavy wheel attached to a stick through its center. When the wheel is not spinning, the stick wobbles and falls over. When the wheel spins fast, something strange happens. The stick stays upright. It resists falling. This is not magic. It is a property of physics called angular momentum. Angular momentum is a fancy term for the stubbornness of a spinning object. Think of it as the spinning wheel's refusal to change what it is doing. A spinning top stays upright because of angular momentum. A spinning bicycle wheel stays balanced because of angular momentum. The faster the wheel spins, the more it resists being knocked over. This resistance is what keeps the ship steady. Here is a simple picture to remember. Picture a stickman riding a bicycle. When the bike is still, the rider falls over. When the wheels are spinning, the rider stays up. The same trick is happening inside the ship, only the wheel is much larger. Now let us talk about waves and tipping. A wave hits the ship from the side. The force of the wave tries to rotate the ship around its long axis. Engineers call this rotation torque. Torque is just a fancy word for a turning force. When you twist a jar lid, you are applying torque. When a wave pushes a ship sideways, the wave is applying torque. Without help, that torque would tip the ship over. But the spinning gyroscope inside the ship refuses to change direction. So instead of tipping, the ship does something else. It turns a little in a different direction. This sideways reaction is called precession. Precession is the gyroscope's way of pushing back. Imagine you try to tilt a spinning bicycle wheel by pushing the axle sideways. Instead of tilting, the wheel fights you by twisting in a new direction. That twist is precession. The same physics works inside a cruise ship. A wave applies torque to one side of the ship. The gyroscope responds with precession in a different direction. The precession pushes the ship back toward level. The wave is stopped, the ship is steady. This is gyroscopic stability in action. It is the same physics that keeps a satellite pointed in one direction in space. It is the same physics that keeps a Segway upright. It is the same physics that lets a quarterback throw a perfect spiral. All of these rely on the stubbornness of a spinning wheel. Inside a ship, this stubbornness translates into a calm ride. The bigger and faster the gyroscope, the calmer the ride. So engineers build enormous ones. Buoyancy keeps the ship up. Gyroscopes keep the ship steady. But there is one more design trick that ties it all together. Engineers control the center of gravity. Center of gravity is the point where all the weight of an object balances out. For a ship to stay upright, the center of gravity must sit very low, lower than the buoyant force pushing up. If the center of gravity sits high, the ship becomes a top-heavy tower. Top-heavy things fall over easily. So engineers place all the heaviest items at the bottom of the ship. The diesel engines go in the lowest level. The fuel tanks sit below the passenger decks. The water treatment systems go near the hull. All the heavy machinery is packed into the lowest possible space. The passenger cabins, pools, and restaurants sit high above all that weight. But because the heavy weight is at the bottom, the whole ship acts like a Weeble-Wobble toy. A Weeble-Wobble has a round bottom filled with dense material. Push it sideways and it pops right back up. A ship is built the same way. Heavy at the bottom, light at the top. Waves can push it. It still rights itself. Now let us look at the actual gyroscopes used in real ships. Some older or specialized ships use a massive spinning flywheel. A flywheel is just a heavy disc that spins very fast. Imagine a metal disc the size of a small car. It spins thousands of times each minute. These flywheels sit in vacuum-sealed spheres deep inside the ship. The vacuum removes air so the wheel does not slow down from friction. As the ship rolls, sensors detect the angle of the tilt. The flywheel is tilted slightly in response. The precession from the flywheel pushes the ship back to level. It is like a giant invisible hand keeping the ship upright. Modern cruise ships use even more advanced systems. They use precision gyroscopes that act like the ship balance organs. These gyroscopes do not just spin, they also measure rotation perfectly. They tell the computer exactly which way the ship is tilting and how fast. The computer reacts in milliseconds. Here's where the engineering gets really clever. The computer sends a signal to large metal fins on the side of the hull. These fins look like the wings on an airplane, but they are underwater. They extend outward from the ship near the waterline. When a wave pushes the ship left, the fins pivot like ailerons on a plane wing. An aileron is a moving flap on an airplane wing that controls rolling. The fins use the ship forward motion through water to create lift. Lift is a sideways force here, not upward. The lift pushes the ship back to level. The wave tries to tip the ship one way. The fins push back the other way. The result is a ship that feels almost still, even in rough seas. Passengers can drink coffee without spilling. Waiters can carry trays without dropping them. All thanks to spinning wheels, sensors, and underwater fins. Physics doing its quiet work. So let us recap the entire trick. A steel ship floats because it is a big bubble full of air. The water it pushes aside weighs more than the ship itself. The ship stays upright because of low center of gravity and spinning gyroscopes that fight every wave with precision. That is the quiet physics that lets a floating steel skyscraper cross the ocean. Thank you for watching this video. Let me know in the comments if you liked it. Don't forget to like and subscribe for more.